All right, the recording has started, and we will begin the lecture. So last time we talked about relations, and today we're going to talk about like a special class of relations. And fortunately, you are very familiar with this. They're called functions, right? So what is a function? Well, it's a type of relation, right? Such that which is and we know a relation is a subset of A cross B, right? The Cartesian product. Well, a function is a special class of relation such that, every guy, right, needs to show up. Every guy in A needs to show up, right? And every guy in A can only show up once, right? So what does it? And that's basically what is going on over here. For all A in A, right, there exists a unique B such that AFB is true. Okay, so that is that's encapsulating what I just said, right? And A, and we write it in this special notation, right? You can use \2, and A in this the set A is the domain of F, and the set B is referred to the codomain of F, right? So if you took like let's say calculus, right, or even high school pre-calculus or whatever, you might be familiar with the term domain and range, right? But range is a little bit different from the concept of codomain. In a range, I think I hear something. Okay. I think I admitted them. Okay, cool. So where were we? So the concept of range is a little bit different from codomain, right? Not everything in the codomain might get hit, right? But a range is a subset of the codomain such that stuff gets hit. Okay. The other notate thing is like remember when we had relations, right? We would use this type of thing, or sometimes you would just use R also. So that means but like we wouldn't use like this notation over here, right? That's weird. You just use f of a is equal to b, right? Which would and this is equivalent to, right, saying that a comma b is in R, right? Cool. And recall from the first homework that if you have an exclamation point here, it signifies uniqueness, right? So for every single guy in the domain, there is a unique um, unique element of the codomain such that A is mapped to the codomain. That I should also mention that there are authors who use, instead of a function, use the word map or mapping. Okay. Well, and there are some contexts or books where the idea of a map and a mapping, or mapping and functions are different, where a map and a function are different, but in most contexts they are basically the same notion. I should also tell you the other notation, right? If you have like f of x, right, is equal to, right, or f of x, right, then another notation you can use is x and this bar over here in f of x, right? And this symbol over here is map \maps2 in LaTeX. Okay. So that's a lot of stuff. So let's actually look at an example. The first example, if we let these two sets be the same, the domain and the codomain be the same, then f be the set of a comma a such that a is in n. Well, this is the identity function, right? As you probably know in well, what am I trying to say? As you probably saw in calculus or pre-calculus or whatever. And the identity function is very, very important because, well, it just is important, right? It's from this that you can basically build up different concepts like the inverse and stuff. And to use this notation that we introduced, right? In this example, we would write f goes from n, right, to n, right? Whereas f of x is equal to x, or maybe I should write n instead of x, right? Because these are natural numbers, right? Or you can also write n maps to n. Okay, great. Right. Um, now let's look at a non-example. If we let A and B be Z, right, and we look at this equivalence relation, right, of mod 3. Sorry, we didn't change the notation, but this is mod 3, right? This is not a function because 1 and 4 is in this relation, and 1 and 7 are in this relation, right? Because since 1 is congruent to 4 mod 3, and 1 is also congruent to 7 mod 3. Okay, so that is a non-example because for this particular choice of integer, right, we found two elements in the codomain that map from that map from 1. Okay, are there any questions so far? Let me look at the chat. Okay, I don't think I see any questions, so I'm going, maybe I'll wait a little bit more. Okay. I think I'm doing decent on time. So let me just give you two more examples of what I think are important functions. So if A is a subset of B, right, then the inclusion map, right, goes from A to B. A lot of authors will just use a hooked right arrow, right? And the inclusion map, let me write it down. This is important in, I think, geometry, topology. The inclusion map is, well, this letter is an iota, by the way. The inclusion map is given by, x maps to x. So nothing too special, but it's basically the identity function, but the codomain is a larger set. And similarly, right, if we have A is a subset of B, right, then you can define, and F is a function from, actually, that's not what I want to say. So if A, well, no, that is what I want to say. What I want to say, A is a function of a subset of B, and F goes from B to C, then you can define the restriction, right, as the follows, right, and this is, I'm going to write it like this. Well, it's basically this is the I think I'm going to write it like this, actually. This is a function going from A to C, right, given by f restriction of A of x is equal to f of x. Okay, so we're restricting the domain from the larger set to the smaller set, but it is going to be it's going to agree such that it's going to agree with the larger function in the larger set, and the smaller in the intersection. Sorry, I should say. And these two you can easily check are functions, because these are just, these are like manipulations to the identity function. Okay. Did that make sense? Did this little digression, okay? And I should mention that the I said the inclusion map is particularly important if you're studying geometry or topology, right? The restriction map is also fairly important if you're studying something like algebra or topology or geometry. The inclusion map is sometimes called the canonical injection, for reasons that we'll see below. But maybe I'm digressing too much. If there are no questions, let's move on. I'm going to move on. Great. I don't think I see any questions. I will move on. So the next thing, so now that I just talked a bunch about functions and we looked at some examples of functions, let's look at these important definitions about ideas about functions. And you probably saw this already in, like, let's say pre-calculus. We say that a function is injective, right? Or we say it's also one-to-one. Sometimes you'll write just one-to-one. If for all x, y, and a, if they agree on the function value f of x equals f of y, then that implies x is equal to y, right? You can sometimes it's useful to consider the contrapositive, which says x is not equal to y implies f of x is not equal to f of y. Okay, so if you have two different elements in the domain, then they will map to different places in the codomain. And what that means is that every element in the domain will map to, well, every codomain, every guy in the range, every element in the range or the image will have a unique pre-image. But we're going to get to that, return to that idea a little later. So let's look at an example. The identity function that we saw from before is an injective mapping, because if x and y are in the natural numbers and f of x equals f of y, well, then x equals f of x and f of y is equal to y, so x equals y. Right. I'm not really particularly fond of this example because it's too easy. But you can look at something like, I don't know, 2x, but that's not particularly enlightening. I think, yeah, usually when you would, in pre-calculus or something, if you wanted to see if a function is injective or one-to-one, you would use something called the horizontal line test, right? If you remember. Because if you fail that, right, let's say I'm going to draw something over here. Say the graph looks like this. I don't know. Then the horizontal line test says if a function is injective, then for every horizontal line you draw, right, it'll only hit the graph of the function only once, right? But if it hits the function twice, then you know it's not injective because you found two places where the where you found an element in the codomain where two different elements, or at least two different elements of the domain, map to that element in the codomain. Okay, and as an example, we can consider the function going from r mapping to -1, 1, given by sine of x, and it's not injective because it looks like a wave, right? It's a sine wave, and clearly, if you draw like a horizontal line, it fails the horizontal line test. And we can also exhibit the two different elements in the domain. F of 0 is equal to f of 2 pi, right? Because they're both 0. Sine of 0 is equal to sine of 2 pi equals 0, and 0 is not 2 pi. Okay? All right. And the next concept we're going to talk about is the concept of surjective mapping, or surjective function. Surjective, we also say that a function is on to B, right? Excuse me. What I learned was proper, right? When I learned this, is that whenever you say onto, right, then you need to show which set you need to show the codomain. Basically, you need to show what the function is mapping onto. But a lot of authors just don't write the second part. Okay, this set will be omitted. And what it is if for any y in B, right, there is some x in A such that f of x is equal to y, right? What that means is every element in the codomain gets hit by f. Okay. As an example, I really don't like this example. What the heck? What is it? If f goes from r to 1 comma 1, right, given by f of x is equal to 1, is a surjection because this is a singleton set and f of 0, and you can always find an element in the domain such that it maps to 1. Right. And as a non-example, right, you can consider x squared, because we showed earlier in the earlier lectures that there's no element in the real numbers such that x squared is negative, right? So the negative numbers don't get hit, and particular -1 will not get hit, and so this function is not surjective. Right. So if I might digress for a little bit, if you want to show that a function is injective, right, then usually just using this criterion will suffice, right? But if you want to show that a function is not injective, then you need to show that the negation is true, right? So that means you need to show, right, the existence of x and y in A such that f of x is equal to f of y, right? And I'm gonna write parentheses here, and x is not equal to y, right? And similarly, right, if you want to show that f is surjective, then you need to show that for all y in the codomain, right, then you can find an x in the domain such that f of x is equal to y, right? Or if you negate this, the denial of this would be, and if you want to disprove something, you need to show the denial is true, right? So you need to show negation is true, right? So, and its negation would be when you flip the quantifiers, right? That means there exists a y and b, so that means there's a guy that doesn't get hit in the codomain, right? Such that for all x in A, right, f of x is not equal to y, right? Okay, does that make sense? If the non-example, right, if in the non-example, oh, are you talking about x squared? If f was from r to r greater than 0, would it then be a surjection? Yes, it would, right? In part, and how would you show that it's a surjection? Why don't we take a moment, right? If we have f goes from, let's say, r to r greater than 0, f of x is equal to x squared is a surjection, right? You want to show that it's a surjection, right? And so that means you need to prove a for all statement, right? Well, how do you prove a for all statement? Well, you would need to start by let y be an arbitrary non-negative number, right? Well, then take well, it's non-negative, so it's square root is defined, right? Take x is equal to square root of y, right? Then y squared, what am I saying? X squared, right? X squared is equal to square root of y squared, which is equal to y. Okay? And since our choice of y was arbitrary, we are done. Okay? And we know that this is, and this choice works. You notice, right, that like it doesn't matter how many elements in the codomain satisfies this, right? We could have done like let x equals minus y, right? But all you need to do to show that something is surjective is to show the existence of one element, right? So you don't need to go through the element of like, then you can, you don't need to put in the work of saying like, oh, then you can You can but you can also make x equals to minus square root of y, right? Whereas, maybe in like pre-calculus or calculus, you might have done that, but okay. Is that okay? Maybe a brief review of how we would prove such things. Great. Are there any other questions? I don't think I see any questions. All right. I'm going to move on. So the next definition is maybe the culmination of these two things. So we say that a function is a bijection, right? Bi meaning two, as in bicycle, or a one-to-one correspondence if it is both a surjection and an injection, or if you would like, it is both one-to-one and onto the codomain. Okay. As an example, this function of f going from r to r, f of x is equal to negative x cubed, is a bijection. And as it turns out, I think one of your homework questions asks you to find a bijection from the reals to reals, and Adam just gives you one over here. Probably not the most not the most smart, clever thing to do there, but here's an example. Please try to come up with a different example. There are plenty of bijections out there. And as a non-example, f of x, why did I do this, is equal to arctan of x. This is not a surjection because arctan looks like this, right? Or if you're not familiar, arctan is the other word for inverse tangent. But it has the added benefit of not using the dreaded -1 notation. It looks something like this. The diagram is not to scale, but you can kind of see, right? This is not a surjection because I think -10 doesn't get hit by arctan. So notice, right, that in order for a function to be a bijection, you need to fulfill both conditions, both surjection and an injection, right? So here in this particular example, f is injective but not surjective, and therefore it is a bijection, right? Or it is not a bijection. What am I saying? On the other hand, you can construct an example that is not an injection, but it is not an injection, but is a surjection, right? Or you can construct an example that is neither an injection nor it is a surjection. So there's different ways you can break bijectivity. Okay. So is that okay? The idea of a bijection and the idea of injection, surjection, and bijection will be very important come the next section. And when I say the next section, I mean the section when we do cardinality. So I suggest that you might want to spend some time coming up with more examples or really thinking about what these really mean. Okay. The homework this time around isn't the homework for this lecture. I don't think is too hard, but a lot of it would be just come up with an example, come up with an example, come up with an example. So you will have decent amount of practice coming up with examples or counter examples. Are there any questions? Before I move on to the next topic. I don't think I see any questions. I'm going to move on. That's not what I want to do. So, so you did. This is again another familiar concept because you did calculus, and so if you have f going from a to b and g going from b to c are functions, right? Then their composition is going to be we write g circle f, right? We write in LaTeX it would be g circ f, it goes from A to C given by G. This function is G of f of x, and whenever we discuss compositions, it is I think, or whenever I whenever someone teaches about function composition, it's a crime not to draw this little diagram. All right. So if you have sets, these are all sets. This is A, B, and C, right? Then F, right? F maps from A to B, and G maps from B to C. Then then you might have, this is, let's say, X. Then you have, this is f of x, right? And then this maps to G of f of x. Okay. So whenever you read this, right, you apply the function on the right first. Okay. So you apply f and then you apply g. You read right from left. Okay. No questions about this definition, right? You probably all saw this from calculus. I expect that I anticipate that you probably know all this material already. Okay, so our first proposition of the day just says the composition of surjective mappings is a surjection. Okay, and this is not too hard to prove. So we want to show that G composed with F is surjective, right? So and to prove this thing, we need to prove a for all statement, right? So how do we begin? Well, we begin by just letting a Z and C be arbitrary, right? And we will need to exhibit an X and A such that G composed with F is X is equal to Z. But since G is surjective, right, you know that there exists some Y in B such that G of Y equals to Z. And but F is surjective, right? So you can pull that back further. So there exists some X in A such that F of X is equal to Y, right? Then now we have, right, G composed with F of X is equal to, well, G of f of x, right, by definition, but f of x was y, and G of y is equal to Z from construction. And so we found the desired x. And since our choice of Z was arbitrary in C, that means we are done. Are there any questions about this proof? I'm not going too fast, am I? Great. I'll move on. And the natural question you might want to ask is, right, so we prove something about surjectivity, right? Is a similar proposition true about injectivity? And it turns out the answer is yes, right? If you have two injective functions, right, f going from A to B and g going from B to C are injective, then their composition is also injective, right? The proof is similar and not particularly enlightening, so it is, well, it's enlightening, right? But I don't really want to spend time doing it because it's fairly similar to the proof of proposition 7.7. So we'll ask you to prove it as an exercise. Okay. And of course, as a corollary to this, that just means if you have two bijections, right, then their composition is bijective, right? Because, because proposition 7.7 says these are both surjective, and so their composition is surjective, and these are both injective, so their composition is also injective. So that means the composition is both injective and surjective, right? And therefore, you have bijectivity. Okay, and the idea of the composition of bijective functions being bijective is going to be very, very useful in the next section. It'll come up over and over again. Okay, we're going to use it a lot of times. So it is very important that we have the proofs ready. Okay. I don't think I see any proofs, or not proofs, objections or questions. I'll move on. So the next thing we're going to talk about, we're going to talk about images and pre-images of functions. And the idea is that you can overload operations And what that means is we're going to use the same symbol to mean different things, depending on the context and depending on what we feed it, okay? Okay, so our first definition, right, is let f go from A to B, right? Then the image of x, if x is a subset of A, is all the set, right? All the set of x such that x is an x. So everything that gets hit, right, of everything that gets hit by elements in this subset x. And we write this as f of x, or big X, right? Notice how we have instead of like an element, right, we have a set. I think there are some professors or authors who, when we're talking about function images, right, then we just write brackets instead of parentheses to avoid confusion. But I don't think most people actually do this. Okay, and let's look at an example. If we go back to our favorite function x squared, right, then the image of the positive reals is the positive reals, right? Because if for every positive real number, we can find a for every positive real number, we can find an x, right, such that that f of x is equal to that positive real, and the reverse inclusion is even easier because the square of a positive real number is always a positive real number. Okay. Okay. The next thing is, oh my god. Okay. don't do this. Don't write this. If you have a function f going from A to B, right, then we say the image of f, right, or we can also write the range of f, right, our familiar word from calculus is the image of A itself, right? So we can write, you would write f of A, or you write image of f, but don't use math or m, use operator name, right? And if you have math tools, the math tools package, right? Then \im is included in the package. Although, what the heck? Someone wants to join. It is Adam. Hello, Adam. Right. So don't use math rm when you should use operator name, because operator name will not screw up the spacing while math rm will. Okay.
Seems like I joined at a perfect time to say that doesn't matter.
This is very important because
it doesn't matter. It doesn't change the math whatsoever.
Because whenever you have like a function, right, math rm will not have a space between the variable and the function, but operator name will include the function. Alternatively, you can include in your preamble \declare operator, declare math operator, and you can declare whatever you want. Okay? Or you can just import math tools and use \im. Although this \im is for complex numbers, when you want to denote imaginary parts of a complex number.
This has nothing to do with the lecture.
Okay.
I came here to learn math.
Also, I think it's also actually no. That we can talk about that later. All right. So enough of that digression. So let's look at an example. In the function f of x equals x squared, the image of f is the non-negative real numbers, right? And you can do the set inclusion if you'd like. You can prove that rigorously if you'd like using set inclusion, but I'm not going to bother. And as another example, right, a function is surjective if and only if its image is equal to its codomain. This is basically by definition. And there's nothing much to say here. Are there any questions? So nice of you to join us, Adam, from your coding dungeon.
Yeah, I got bored for a moment.
Okay. All right. It seems like there are no questions so far. Great. Um, don't listen to Adam and his garbage latex propaganda.
Who cares, man? I've never seen somebody who cares so much about LaTeX. I think about it.
um, okay. So our next definition. Well, if you have if you have the image, then the natural thing to think about is the pre-image, right? And the idea of a pre-image, right, turns out is fairly important when you do like real analysis, because pre-images a lot of the times behave a little bit more nicely than function images. And you'll see some examples of this in your homework when you will be asked to prove or disprove some properties about pre-images and images, right? And as a hint, images don't work nice, pre-images will work nice. Okay, so what is it? It is the set, the pre-image of a subset of the codomain is all the set all the elements in the domain such that f of x lands in that subset. Okay, and you write this as f inverse of y, right? Let's see. And
Hey,
don't
I
be
have a quick
confused.
question.
Sure.
Have you been drawing those pictures where you have like like two ellipses where one is the domain, the other is the
This?
codomain?
You mean this picture?
Oh, wonderful. Yeah. I think might be helpful to do that for pre-image.
Sure. So the pre-image of a set, right? If you have, let's say this is A, let's say this is B, right? And let's say F maps over to over here. And let's say this is a subset of A, right? Or B. Let's call it, I don't know, Y. We call it Y or something. Then the pre-image you can kind of imagine is like a pulling back. You pull back all the elements. You pull back all the not elements. You pull back all the guys that get hit in Y, and you what is it? You pull back all the elements, and so
It's hard to say it
everything
in
in here,
words. I think the
yeah,
picture is kind of good enough. If you start with Y as
everything
a
in
subset
here.
of B, then the pre-image is just everything that eventually ends up in Y and nothing else.
Yeah, sorry. I was like, my dad walked in. I was like, then I froze. I was like, like I don't know what to say anymore. Oh, something is when we talk about images and pre-image, image and pre-image. You should specify if it's clear. Like if there's only one function, you can just say like the pre-image.
Yeah.
But
Wait,
you
can you
should
say pre-image of F? What does is that?
no. You would usually say pre-image of a set, right?
Yeah.
Pre-image of F or um pre-image
I've
of
never heard
a
pre-image of F. I've heard
yeah, no.
image
You
of
would
F.
usually pre-image of a set. You would say
Yeah.
like pre-image of a set. Like I think it's under a function, but like usually it's gonna be clear. Um, Usually I just write its pre-image. Just be done with it because in the context it should be clear if you're writing clearly. Okay, does that make sense?
Yeah.
It basically comes down to like how well you're writing. By the definition of a function, do we have the pre-image of f of b is just the domain?
Yes.
Yeah, that's true. I think that's
Because
true.
every element in the
Yeah.
domain ends up somewhere in the codomain.
Mhm. Um, but like if you compose like image and pre-image, some things might not like things might not work out the way you think it might, right? Some you might like the set. I think the set equality I don't think always holds, if that makes sense. This is your homework question, so I'm not going to talk about it a little bit more.
Okay, I was
Okay.
about to say something, but my bad.
This is a homework question, so I'm not going to spoil the answer. But some things might not be as nice as you want it to be. Okay. Are there any other questions? Like, I think I'm giving hints, a lot of hints on the homework right now. Like by
That's
saying that things are
fine.
not as nice as you would like it to be.
Also,
Okay.
I'm just gonna stick this in there before I hop out of here. Pay special attention to relations and functions. They are very important, most likely for your proficiency exam.
Oh yeah, I think like it's like probably like the most important part of 300
Yeah.
because you need to walk out of 300 with with a very good knowledge of, well, set, like you will, all right, you will definitely see a question showing set equality or set containment or something. You will definitely see a function, a question with regards to some kind of relation, either it be an equivalence relation or a partial order.
Hmm.
You'll definitely see a question regarding a function, an injectivity, surjectivity, bijectivity, or inverses. Okay,
Yeah.
or inverses. You will definitely see those questions, right?
Yeah.
Um, and the specifically the question, the exercises in this homework, Adam doesn't like some of them because they're very tedious, and I agree to
Yeah.
an extent. They're very tedious, but these are like the questions in this homework are is the type of
I
is the
would
type
say
of
they're all
problem.
fair game. They're all fair game to appear on an exam. I would say
Yeah,
that.
like that type of question is the type of question to appear on an exam. I want to
Yeah,
say
and even if it didn't appear, I would say that you definitely would expect a 300 student to be able to chug that without any problem,
yes.
because that's very fundamental, is function stuff. Because like later on, like analysis, obviously, and algebra, literally any course afterwards, this will show up a lot. So this is like the most important stuff, basically.
Yeah, this is, yep. A lot of this shows up in analysis, and if you know me, I like real analysis.
Yeah, I mean, in topology too, and in algebra, when we talk about functions as algebraic objects, like all of this stuff. So yeah,
Yep,
it's
yep.
super important. Yeah. Okay. All right. Sorry for the digression, but I'll hop out now, I guess.
All right, this is very important. Where were we? Oh yeah, so the pre-image of y. Let's say, why don't we look at an example? Maybe an example, or if you have an injection, the pre-image of any element, any single element, is either a singleton set or the empty set, right? And why don't we actually look at a more concrete example, right? Let's say f of x goes from is equal to x squared. F goes from r to r, right? Then we say the pre-image, right? The pre-image of, let's say a is equal to, like, I don't know. Let's say -2 to 2, right? Maybe instead of a, I should use b for consistency, or y. I think y is the better choice. Y, right? Big Y. Then we say f inverse of y, right, is all the x in R, right, such that f of x is in -2 to 2, right? But what is that? Well, oh my god, I didn't think. I didn't think when I was creating this example. And that's exactly, the set square root of 2 minus square root of 2 to square root of 2. I think that's right. I'm going to pretend that this is right. Okay? Are there any objections? By the definition of a function. Oh, no, we addressed that already. Okay. Is this okay? Gonna drink water. I'm gonna assume that I'm okay. Great. Actually, with my previous question, would f of b be the domain, potentially be the empty set, if it was not a surjection? What? Oh, the pre-image of f of b, right? If it is not a surjection. Wait. So are you talking about the pre-image of f of b?
Yeah, because I'm thinking
So the
if you have.
pre-image of f of b, if it is not a surjection, no, it'd still be the domain.
Okay.
Um,
So I was
Why?
thinking,
Okay. Do you want to explain?
So why would it be the case? Well, let's unpack the definition, right? Usually, with these types of questions, usually what you need to do is unpack the definition and just follow your nose. Okay, so you asked, right? F goes from A to B, right? What is F inverse of B, right? Well, if we're just unpacking the definition, right? F inverse of B is all x in A such that, well, f of x is in B, right? Does that make sense?
Oh, yep.
But
I
what
see
is
it.
this? This is A, right? So it is the entire domain. Okay. But on the flip side, you have like, B might not be, on the flip side, f of A is not B in general, right? Because f might not be surjective, right?
Mhm.
So, yeah. So that's another example of like, pre-images are nice, images are not. Okay. Great. I've about 30 minutes left. How much of we have left in version? Yeah, we're almost done. Okay. So if you have a binary operator, okay, so the next step, so that's basically it for function images and pre-images. And we're going to digress a little bit and talk more about like overloading things. If you have a binary operator, which means an operator is actually a function, right? It takes a set, right? A binary operator is a function that goes from x comma x or x cross x to x, right? For example, the plus, right, takes any two real numbers, right, and maps it to, what am I writing? That should not be a maps to, sorry. It maps to, what am I doing? Maps to x, right? R, and x and y, right, gets maps to x plus y. Okay. So it's a function, right? And you can kind of overload this operator as follows, right? You can write for any a in A, right, and x a subset of A, you define A, the symbol dot x is equal to, well, all the set of A times x such that x is an x, big X. All right. For example, z plus 0.5 or plus 0.5 is the set of all the integers, but shifted by a half. Okay. And similarly, oh, and by the way, this type of thing is called a coset. And this idea will be very, very important in algebra. So it's very important in algebra. And because it allows you to define like quotient spaces. Or it's very important when you do quotient stuff. And I should probably leave it at that before I say something, before I like slip and say something that's wrong. Okay. And similarly, you can like you can write you can use the operators between sets like so. Okay. Are there any questions? I don't think I see questions. Okay. So now we're going to talk about inverses. Okay. Specifically, we have the notion of a left inverse and a right inverse. And let me just interject with, let me just stop and clarify some notation. If A is a set, right, then we write ID sub A is the identity function on A. So what that is ID A goes from A to A such that X gets maps to X. Okay. Okay. So let F be a function going from F to B, and G going to be a function from B to A. All right. We say that G is a left inverse of F if G composed of F is the identity function on A, right? Let me just draw some diagrams, because this is I think this is very confusing without diagrams. So let's say we have two sets, A, and we have B, right? And we have F going from A to B, and we have G going from B to A. Okay. So if you have, we say that G is a left inverse of F, right? If G comma F, or G composed with F, right? So what that is doing is we're going from A, right? A to B back to A. And if you have that, and that composition is the identity function in A, then you say G is a left inverse of F, right? And then we say G is a right inverse of F, right? G is a right inverse of F, right? If you have G goes from B to A, and then you apply F, right? And then you have that is the identity function on B. Okay, G goes from B to A, and F goes from A to B. That is the identity function on B. So as an example, right, if you have the function f going from n to n, given by f of n is equal to n plus 1, right? Notice that this function is injective but not surjective. That'll be important. And the function, this function given by g of n is equal to 2, piece defined piecewise if n is equal to 1, and n minus 1 is n is greater than 1. And why do we do this? Because n minus 1, right, for if n equals 1 is not defined, right? Because 1 minus 1 is 0, and 0 is not in the natural numbers in our world. So it's not well defined if you just have n minus 1, right? Then G composed with F is the identity function on n. Why? Because f of n is n plus 1, right? N plus 1. And so whatever the image of f is all the natural numbers that's at least 2. So if you apply G to it, you will have to, because n plus 1 minus 1, right, is n. And that's the identity on the natural numbers. However, you have G is not a right inverse for f because, right, f composed of G of 1. Well, what is that? G of 1 is 2, right? So that's f of 2, right? But f of 2 is 3, right? And that disagrees with the identity function, or identity map, or identity function at n equals 1, right? So that means, right. Similarly, right, you can basically flip this argument to show that f is a right inverse of G, right, but f is not a left inverse of G. Okay? Are there any questions? I think left and right inverses is probably the most confusing concept of this entire section, so I wouldn't not be surprised if there are questions relating to this. Didn't we show that it disagrees with IDN at n equals 2 because f of n? What is this? So this entire discussion shows that G composed of f with f is the identity, right? G composed with f is the identity, but, right, f composed with G is not the identity, right? So if you look at this definition, G composed with f is the identity. So this is a left inverse, but it is not a right. So G is not a right inverse for f, right? But if you flip the definition by just swapping G and f around, that means f is a right inverse of G, but f is not a left inverse of G. Does that make sense? Didn't we show? Yeah, we're showing that it disagrees with the identity function, right? Does that make sense? Is the confusion cleared? Cool. Right? Are there any other questions? It's very this is very confusing. I always need to like think about like what Like I always get confused between left and right. um, okay. Cool. So a function with a left inverse might not always have a right inverse, right? And vice versa. Okay, great. I'm going to move on. So how do we determine if a function has a left inverse or not? Well, fortunately for us, there's a proposition. A function f going from a to b is one-to-one or injective if and only if there exists a left inverse. And this might be a little bit surprising, right? Because, well, it might not be surprising if you know, like, that a function is invertible if and only if it is bijective. But let's prove this because we are starting to run out of time. Okay, so let's do the forward direction. Suppose f going from a to b is one-to-one, and for each y in the image of f, right, that's a subset of b, there exists a unique x in y in x in a such that f of x is equal to y, right? So that means this allows to define a function g going from the image of f to a using this rule, right? Send each y in the range or in the image of f to its unique pre-image in a, right? Because right, that makes sense. Now the idea will be we're going to extend the function to b, right? So let me draw a diagram, right? So I have a over here, and we have b over here, and f maps all of this to maybe, we don't know what kind of set, but it might be some subset, right? But it maps this subset to b, and since f is injective, we can kind of pull this function, pull this image back, and that kind of inverse that inverse from the image, right, is going to spit out a unique value in a. Okay, and you can do this because it's one-to-one, right? Because you can every guy in here is paired with a unique guy in here. Okay, and the idea will be to kind of extend this, extend the function, right, to take values in all of b. Okay, and you can basically do this however you want, but you can just say let x0 in a be arbitrary, then now define g star going from b to a by, like, g star going from well, just such that it agrees with y, right, in all of f of a, and just send it to x0 if it's not in the image, right? So you need to show that this satisfies the desired properties, right? In particular, you need to show that it is the left inverse of f. Okay, so let x is in a, right? Then g star composed with f of x is equal to g star of f of x, right? Well, but from the definition of g star, right, that's just x, right? And that's the identity function on a. And so that means we have verified the existence of the left inverse. Okay. Suppose f, not for the reverse direction, we're going to suppose f has a left inverse, we call it g, and suppose there are x1 and x2 in a such that f of x1 is equal to f of x2. We want to show, right, f is injective, right? And how do we show injective? We need to show that for all x1 and x2, right, f of x1 equals f of x2. We want to show that this implies x1 equals x2, right? So well, so we begin with this begin with this hypothesis, right? Then what you do next is you apply g to both sides, right? Then g composed with f of x1 is equal to g composed with f of x2, right? Like this. But since g is a left inverse for f, g composed with f is the identity on a. So that means x1 is equal to x2 because this left-hand side is x1, and the right-hand side is x2. Okay, and that shows that f is injective. Did this proof make sense? On the other hand, right? So you might be wondering if the other hand, the flip side is true, right? A function is surjective if and only if there exists a right inverse, right? Well, it turns out it's true, but right, you need the axiom of choice for one of the directions. It's easy to show the backwards direction. It's very similar to our work in the backwards direction over here, but the forward direction actually requires the axiom of choice. You actually need the axiom of choice to show that every surjective function admits a right inverse. Okay. So we're going to admit that because we don't want to touch the axiom of choice, right? You see that coming up multiple times now, right? We think the axiom of choice came up with what was it? The well-ordering theorem, and now it's coming up in the existence of a right inverse. So we'll just take this fact for a given. Okay. Now, right, so we talked about left and right inverses, but we haven't actually talked about, the actual thing is the inverse of a function. So let f going from a to b be a function. We're going to define the inverse of a function to be, f minus 1, f inverse, right, the symbol, going from b to the power set of a. And why do we do this? Because, well, different, if it's not one-to-one, right, if the function is not one-to-one, then like different guys might, and different elements might end up at the same element in the codomain, right? So if you have a and b, let's say here's x1 and here's x2, but these guys might end up at the same place over here, right? By f. F might map here, and f might map here. Okay? Then that's why we would define it to be the power set. So we just define it to be the set encompassing these two elements. Okay? With the notion of pre-image that we defined. Of course, if f is 1-to-1, there's no need to do any of this, right? But on the other hand, right, the inverse is not defined, well, right? But if f is not surjective, right, then what are you going to do with this guy that doesn't get hit by f? Well, then the pre-image would be an empty set, right? And that wouldn't be then that would be sad. We'll talk about how to get around this if we have time. Okay. So we will say that f is invertible if each of the pre-images is a singleton for every y in B. Okay, so that just said, so in this case, the inverse would be a function. We can define inverse to be a function going from B to A if it's invertible. Okay. Note that if a function f is invertible, then its inverse, right, is both a left and right inverse. And that's another definition of an inverse. We say that inverse is a function g, right, such that g composed with f is equal to f composed with g is the identity. Or wait, what am I saying? That is not what I want to say. That's like groups, or automorphisms. Is the identity f identity on A, f composed with g is the identity on B. Okay. And there's a theorem that says the function f going from A to B is invertible if and only if it's a bijection. Well, if it's invertible, to show it's a bijection, then you would need to show it's both a surjection and an injection. And you can just do that. I think it just follows straight from the definition, right? Yes, it should. Because yeah. Let's see. And well, this paragraph isn't that important. Let me just give you a sketch. So let's show that this direction is true, right? Suppose f is invertible, right? So G goes from B to A. I'm gonna omit some details. Is its inverse. Let's show injectivity. Suppose x1, y1, or what am I saying? I'm gonna forget it. I'm just gonna use x and y. X, y are in A such that st that means such that f of x is equal to f of y, right? Then, well, what would you do? You just apply the inverse, right? So G composed with f of x, right? This is very similar to our work above, right? Well, but what is this? This is the identity, and this is the identity. So x is equal to y. Okay, so that shows injectivity. And to show surjectivity, let z be in B and be arbitrary, right? Well, then what would you do, right? Then the inverse exists, right? It's the G is the inverse, then G of Z, right? Well, G of Z is in A. Well, f of G of Z, right? Which is f G Z, right? Well, what is this? This is Z. So that shows surjectivity. Cool. Are there any other questions? No. And to show, and so that shows this direction. The other direction, right, is exact same thing over here. Just do this construction, except, right, you're not going to need this part because this case is just never going to be satisfied, right? Every guy is going to be in the image. Okay, so there's no need to do this. Or yeah, to be more precise, we can just use because it's 1-to-1, right? You can just find the unique guy that you send to. And that's just the sketch of the proof. Okay, that is going to be that concludes the discussion on inverses. Are there any questions on the material so far? Because the rest of the material I'm going to talk about today is just going to be like some wrap up. It's not going to be particularly important. Is the speed okay? Great. All right. So, all right. So recall, right? The very first thing we said a function is a relation, right? And that means, right, from the definition of a relation, if a function goes from A to B, that means f is a subset of A cross B, right? And that means we say f of x equals to y if and only if x comma y is an f. That means we can think of a function as a set, and in fact everything is a set, right? And this gives us kind of a neat way to think about how we say when two functions are equal. Okay, in fact, how do we say two? Then we can say two functions, let's say f and g, right, are equal if, well, f subset is a subset of g and g is a subset of f, right? For every x comma y you can find an f, you can find x comma y in g, and vice versa, right? On the other hand, right, and this allows us to give you another criterion to show how to see if functions are equal. You need to check that the domain of f is equal to the domain of g, and for all x, and for all x in the domain, right, whatever, of f, if they're equal, right, f of x is equal to g of x, right? and you might be wondering why this first criterion is necessary, right? Well, but this might but if you don't, if you omit this criterion, right, then the inclusion map that we talked about earlier, right? Well, then if you omit the criterion, just check that the functions are agree on values, then the inclusion map and the restrictions turn out to be the same as the original functions, right? In particular, the inclusion map would be the same as the identity function, and the restriction of a function would be the same thing as the original function. And you obviously really don't want that, right? Okay. In fact, right, the notions like domain, codomain, image, composition, and inverses, we can define these things for relations, not just functions, right? The inverse of a function, or you would define like this, right? In fact, you can define the inverse of a relation like this, right? If R is a relation, then you can just write, R comma X, right? Such that X comma Y is in R, right? Composition would be defined X comma Z and A cross C, such that X comma Y is in F and Y comma Z is in G. And you would define the composition of relations like the same way. S composed with R would be, X comma Z, such that X, Y is in R and Y, Z is in S. Okay, so these, some of the notions we talked about are not unique to functions. We can also define them for relations also. So you can, in fact, you can define these for relations. Okay, are there any questions about this discussion? Okay, I don't think I see any questions. So maybe I'll talk about function restriction for a little bit, and then that'll be it. So if you have a function, right? Let's see. So let's talk about f of x is equal to x squared. This thing is not injective, right? Or it's not surjective, but like if we let's say we go from f goes from r to, let's say, r greater than 0. Right? Now it's surjective, but it's not injective, right? Because it looks like this. And we don't, and whenever a function is not injective, then we have some problems with defining the inverse, right? So how, but like if you, but the idea to define like an kind of an inverse for this will be to just restrict f to the f to a smaller subset, right? Well, now it is injective, right? In fact, it's bijective, right? If now f going from r greater than 0 goes from r greater than or equal to 0 to r greater than or equal to 0, and it looks like this, right? And now we can define the inverse, right? The square root of x function is kind of the inverse of this function. When you have like a function that doesn't quite satisfy, or when I say has an inverse, I mean invertible. So like when you have a function that doesn't quite satisfy the property that you want it to, so one strategy we do is to just restrict the function to like a suitable domain, and that's precisely the idea you do with sine, cosine, and tangent, right? You restrict the original functions to define the inverse functions, arcsine, arccosine, cosine, and arctan, right? You restrict these functions. I don't remember actually which interval it is. I think for cosine, you go from you chop off this, right? Because it looks like this, right? So you chop off that. So you only consider this interval, right? And for sine looks like, what does sine look like? This, right? So I think sine, you only consider this part, right? And for tangent, you only consider tangent looks like this, right? So you only consider this one period, right? You restrict these functions and use that restricted map to construct the inverse. Okay? Does that make sense? Are there any other questions? If there are no more questions, then I'll stop the recording.